8.2 lesson. Now, electron configuration can be a bit of a booger, and they don't ask it all that much on the real test, but it does come up. And this is one of those topics that you might have to go around a couple times, even with a couple tutors. Once you see it, it tends to be pretty simple, but I've never found the magic way to get people just to leap to understanding it. So I will do my best here. So electrons sit over the nucleus. Obviously, we have a nucleus, then we have electrons, and in very, very rough terms, they're going around it. Now, there actually is one orbital that's actually round, and it's called the S subshell or sub energy level, or every one of these things depicted here is an orbital. It's a pathway for two and only two electrons. So there could be two in this S subshell, which is a sphere, and then we could have two in this double balloon looking thing here, and that's one of the p orbitals in the p subshell. Then we could have two in this double balloon and two in this double balloon. This does not imply that one of the electrons is here and one is here. Together, they tend to make this shape, though. Now, for the d suborbitals, it looks like four balloons, and then there's this double balloon with a donut around it. And yes, that is weird, and no one ever tried to tell me why that is. But again, each one of these shapes can only hold two electrons. So an S subshell can hold two. A p subshell has three orbitals, therefore it can hold six electrons. A d subshell has five orbitals, therefore it can hold 10 electrons. And the f has seven and can hold 14 electrons. That probably won't come up in any problem that you do. It certainly won't come up on the real AP test. So the periodic table is this shape deliberately to help us do things like find the electron configuration. So each row is an analog for a main energy level. So this is the first energy level. This is the second energy level across here, the third energy level. And then after that, it gets slightly more complicated. And that just means energy level. That's just my notation. That's not official. So this would be hydrogen here, and this would be helium here. And each energy level fills from the bottom. The electrons go as close to the nucleus as possible, and then they build out on each individual atom ever. And we're only going to talk about what is called the ground state here. That's the lowest possible energy levels. So we're going to pretend that all the electrons are as compact as they can be and as close to the nucleus as they can be and as low energy as they can be. In reality, they hop around quite a bit. And the fact that this light is on in this room is because electrons have been excited to some energy level, and then when they drop back, the energy they contained before cannot be destroyed, but it can be released. And what the electrons do as they fall back toward their ground state is invent photons to release packets of light that we discussed in 8.1. So every kind of light, no matter what the technology, I'm using an LED right now, uses the fact that electrons, when they fall to an lower energy state on some atom, have to release that energy in some form, and they like to invent light. And so if you can manufacture this so that it releases the light in the visible spectrum, we have a commercial interior light. So let's just talk about the simplest version. What is hydrogen? The ground state of hydrogen, because it has one proton, that's what hydrogen means, has one electron. And we would symbolize the like this. Hydrogen in the first main energy level, it is using the s orbital or subshell, and there is one electron in it. I realize that looks like an exponent. It is very much not. Please don't say s to the first or s squared. You will look like the newbie and everybody will laugh, frankly. So helium is in position 2 on energy level 1, and this one shows us it's still using the s subshell, and that's because the s orbital or subshell, same thing in this case, can hold 2 electrons, and we have not yet filled it with hydrogen. We will fill it when we go to the helium spot. So here's 1 electron used, and this is 2 electrons used. And yes, I'm counting across the periodic table as an analog for filling the electrons. Let's say that every time we go to another box, we are counting another electron filled in on an atom. So for helium, we would be on the first energy level, still using the s subshell, but there would be 2 electrons in that subshell. For lithium, being the third element, we are on the second energy level. And again, we are in the S subshell. Every main energy level starts with the S subshell. So the S subshell appears in level 1 and 2 and 3 and 4 and so on. The P subshell only appears in level 2 and 3 and 4 and so on. And the D subshell only appears in level 3 and 4 and 5 and so on. So lithium is on main energy level 2, and we are in the S block. This almost a rectangle, if you would mentally move this one over, it would be a rectangle, is where the S subshell is indicated. This rectangle is where the D subshell is indicated, and this rectangle is where the P subshell is indicated. Now, there is the F rectangle. It probably won't come up in anything you're asked to do. So with lithium, we are on level 2, row 2. We are back in the S subshell, and there is only one box we're using. So that means there is one electron that we're using. And that also corresponds with the fact that lithium, again, is element 3. That's 3 protons that it has. And that means it would have 3 electrons. And so lithium would have 2 electrons in the main energy level, the S subshell. And in energy level 2, in the S subshell, it would have only 1 electron, and that's our 3 electrons, 2 here and 1 here. Let's take a bit of a jump. Let's do nitrogen. So we read it like a book, and every element starts back at the beginning. You have to build all the electrons from the inside out. So nitrogen would have electrons at position level 1 S1, level 1 S2, level 2 S1, level 2 S2, level 2 P1, 2, 3. And so the final note we would make is 2P3. Now, in reality, we don't want to have to write all that. So everybody skips ahead a little bit, and we just write the end of the subshell. So we're not going to write 1S1. We're only going to write 1S2, and then 2S2, and that's 4 electrons. And then 2P3, because that's as far as we got in the P subshell for energy level 2 or row 2. So how about we do silicon? So silicon, again, like every element, starts from the beginning. 1s1, main energy level 1, S subshell 1 electron in that spot. 1s2, main energy level 2, S subshell with 2 electrons in it. Energy level 2, P subshell with 1, 2, 3, 4, 5, 6 electrons in it. So let's just take stock right now at the moment. For sulfur, that would be 1s2 and then 2s2. And I'll note that gets me to here. Then 2p6 gets me out here because energy level 2, P subblock 1, 2, 3, 4, 5, 6. But I'm going to read it like a book and keep on going until I hit the block for S. So I'm going to come back down here. Now I'm on level 3, still the S subshell block. 1, 2, 3, S2. And keep going. This is the P subblock. I'm on level 3. So 3P, 1, 2, 3, 4. 3P4, and that's where I'm ending because I have now hit the S spot on the periodic table. The extra little trick to this is that the D subshell is 1 off, and I wish I understood this better entirely, but no one ever asks, including the AP test. So somehow I never quite figure it out because it comes out about 2 days a year, and then I forget about it. But the D subshell is 1 level off. I know that this is row 4. Clearly, it's row 4. But the D subshell belongs, in a sense, back here, and it is part of shell 3. So when we ask, how many valence electrons does chromium have, just to pick one, the answer is not 1, 2, 3, 4, 5, 6. because these last 4 belong in shell 3. And so what we're asking is, how many outer electrons, valence electrons, does chromium have? And there are only 2 electrons in shell 4. So in the ground state, all these atoms in the transition metals under the trough have 2 valence electrons. Now, for you people who are going to actually be something like a chemistry major, that is not strictly true. There are some exceptions, and it gets a little weird under here. And some of these manage to take an electron from the S block and pull it into their D block because it makes a more stable configuration, a less energetic configuration. The AP test is never going to ask you that, and it is a bit of a nightmare to figure out once. I've never even been told a pattern. So if you need to look it up, you can. I'm sure there's a table somewhere, but it's not going to come up for the purposes of high school chem, not even in the AP class. We would consider all these elements down here in the transition metals to have 2 valence electrons because this block, the S block, is their outermost shell. In this case, shell 4, that's row 4, shell 5, 6, 7. Over here, these would all, let's say the halogens, all of them would have 1, 2, plus 5 is 7 outer shell electrons. And that even applies down here because remember, we're ignoring these for the purposes of outer shell electrons. And if you think back to your Lewis dot diagrams, that's why this block was always 7 valence electrons, 6, 5, 4, 3. Now let's talk about orbital diagrams, because this does explain a few things for the real test. We can just use a shape as an analog for the orbitals. So each box is 1 orbital here. I've seen people use triangles and circles too. Each orbital can hold 2 electrons. However, there is one more wrinkle to this. Now, nitrogen, for example, has 2 electrons in the S subshell, but electrons have a further characteristic called spin, and they have a magnetic moment, or they sort of have a north and south pole. Why exactly, I don't think I was ever told, but if we accept that they do, then what they want to do is align their north and south pole oppositely as if they were magnets. And that's usually depicted, it was an arrow, and everybody gets so tired of drawing both sides of the arrow that they just draw one half, and we get an up and a down, and that is our 2 electrons in the 1 orbital, and their north poles are opposite each other. And that will happen again here, both of them in here. And here's the wrinkle. It's true that each orbital can hold 2 electrons. However, because of their negative character, electrons repel each other a bit. They're not going to take up roommates, so to speak, unless they have to. I have 3 spots for 3 electrons, and so each of them goes into its own little room, into its own orbital. It is distinctly wrong to put 2 into 1 room if there is still an open room to use. And not because we think it looks better, it is because that is what nature does. There's something called Hund's rule, which says that each electron in each atom has its own unique set of characteristics. There is no other electron that is 2p X, Y, or Z. This is the X. So this is 2p on the X axis, 2p on the Y axis, 2p on the Z axis. And on this nitrogen atom, there is no other electron that matches any others. Now, before you say, yes, there is, because these are together, then we go to the spin. And this is 1s. They are both 1s, but this one is up and this one is down. So they still don't share all the characteristics with any other electron on that particular atom. This also helps explain something about first ionization energy. That is the energy it takes to knock off 1 electron. And the first ionization energy then is the energy it takes to knock off the first, or usually then outermost, electron. So oxygen would be a repeat. I'm just going to do this, but it would be 2p4. Go look at your periodic table. And so we must do a doubling up there to get 4 electrons in 3 orbitals. Go find a chart of first ionization energies, and it turns out that the transition from nitrogen to oxygen, when we go across from nitrogen box to oxygen box, has a bit of a hiccup in the first ionization energy graph. And it's a little easier to pull an electron off of oxygen than it is for nitrogen. And that's because if you pull one electron off for oxygen, you get this configuration with one electron in each orbital, and that turns out to be slightly more stable than having one paired up. Nature likes this better than that, and so it's not so hard to pull one electron out of here and achieve that. Here's an equation on Coulomb's law that does come up as a concept on the real test. You're not asked to actually calculate using this, but you have to know the basics of how it works. And what this is saying is the force binding charged particles together is equal to a constant, which doesn't honestly come up, times the charge of the first ion times the charge of the second ion divided by the distance squared. What this tells you then, if you understand the math, is as the charge goes up, the force goes up. So more charge is more binding force. And it's going to take more energy to take these two ions apart from each other. They're held together with greater force if they have more charge. +2 - 2 is greater than +1 - 1, or even +2 - 1, 1. And being closer together, having a smaller distance, gives a bigger answer, doesn't it? So if these ions can nestle together closer, that gives them a greater binding force. They're held together more strongly. It's going to take more energy to break them apart. I made a sample problem very much like an actual problem off a release test. Which of these four will have the greatest binding energy? Well, what we have here is +1 - 1 +1 - 1 +2 - 2 +2 - 2. And we said that as the charge goes up, the force holding them together increases, so we can eliminate the +1 - 1s. +2 - 2 is clearly held together with more charge. Between these two, which one is held together with greater force? The charges don't help us anymore. They're both +2 - 2. When we look at magnesium versus calcium, though, which one can nestle in closer to the oxygen? Which one has a smaller distance from center of nucleus to center of nucleus? Magnesium starts on shell 3 and actually, because it is +2, loses these two electrons, symbolized by these two boxes, and falls back to having no shell 3 and only having a shell 2. Calcium also loses 2 electrons and falls back from having no shell 4 to only having a shell 3. Either way, though, even if we sort of didn't know that that was happening, which one is smaller? And the answer is magnesium. Magnesium can come in closer to oxygen, and therefore its binding energy to oxygen is greater than calcium's is. And this is our answer for the greatest force of those four. Now I want to come to photoelectron spectroscopy. Yes, that's a heck of a word. And this does come up a little bit on the real test, and it is a little bit weird. So you might want to hit pause and have a think, and you definitely want to get your periodic table to follow along. So what these peaks represent are the binding energy of the electrons. So we know that the electrons come in 1s2, 2s2, 2p6, and so forth. This graph is a little unusual in that the more energy is to the left. And the more protons your atom has, the tighter these electrons are held on. So as these peaks shift to the left, that means that atom represented on this line has more protons holding those electrons on. So let's take a look at this. This one has one little bump. It is not very well held on. Look at how close to zero out here it is. It would not be very hard to rip this electron off because its binding energy is low. Now, how many electrons does that represent? And I know I said singular because I know what this is. So I kind of gave away the answer. Well, let's compare. Here is a bump that has moved over just a little bit. And if we measure it, I bet that this one is double that one. So what we have here is an electron and only one electron. So that would be represented by 1s1. Now, if you added another proton into the nucleus, we'd have helium, and this would be still 1s, but there would be 2 electrons in there. And the vertical height is the number of the electrons represented. Each peak represents a different subshell, SPDF. We won't get to F. So this would be a different subshell than that one. However, at this point, I know I filled up subshell 1s, haven't I? You can only fit 2 electrons in there. Also, this is the first peak, so this is going to be the 1s subshell. And it's the same height, so that must also be 2 in there. And yet there is another one. Well, what would be the next peak that would come? If we look here, the next subshell that would come after 1s would be 2s. So what we're looking at there is 2s with 1 electron in it. How do I know it's 1 electron? Well, it's half the size of that one. And again, the vertical height represents the number of electrons in that subshell. So this is 2s1. Here's my first peak. That's going to be 1s2. Here's my second peak, but it has grown. Ah, there's another electron in there. 2s2. Here's my first peak. Okay, 1s2. My second peak, 2s2. And yet there is a third bump. What would come after 2s2? 2p. And yet this is half the height of that. Ah, so if this represents 2 electrons with its height, then this represents 1 electron with its height. And that would be 2p1. And in fact, the way this question is phrased, they asked us to write boron. And of course, that would be our answer because boron is element number 5, and it would have 5 electrons. So we would put in 2, 4, and 5 electrons. In reality, on the real test, they would never ask you to draw this because the placement is a nightmare. I don't think I was ever taught how to place them. I know to recognize them, that this 1s peak has been moving over as protons get added and the electrons near the nucleus are held tighter and tighter. It takes more and more energy to break them off. The binding energy has grown. But I wouldn't know where to place this. So this question is unrealistic. Let's pretend that we were just given this answer and asked to identify this element. Even without the peaks below, I can still read this. Let's see, there are 3 peaks, so that is 3 different subshells. That means I filled up the first one, certainly. So this represents 1s2. This is the same height, so it is the same number of electrons, and it must be the next subshell. So it's 2s, and the same height means it has 2 electrons in it. The next peak must be the 2p subshell, and it is half the height, so it must have 1 electron in it. That is 2, 4, 5 electrons. This must be boron. Let's do some samples here too. I know the answers are there, but we'll pretend. Here's my first peak. It matches the next peak. This is 1s2, that's the same height. 2s2, that's 4. This is the same height, so it must also contain 2 electrons. That is 3 bumps of 2 electrons. This element has 6 electrons. It is carbon. This one has 1s2. Yes, let's make sure. Yes, the next one is fully filled, so this represents a 2. That's 4. This must be 2p, and it is double the height, or close enough. Sorry, I realize that may not be exactly true, but on the test, they would do better at it. This is double the height of that one, so this peak represents 4 electrons. That's 2, 4, and another 4 is 8. It has 8 electrons. This element is oxygen. The first bump would be 1s subshell. It matches this one. Yep. Okay. So this bump represents a 2. So 2 here, 2 here, and this height is triple that height. So this is a 2. This is another 2. And this is triple of a 2. This is 6. 2 and 6 is 10 electrons in the ground state. This must be neon. On number 5 here, we're asked about lithium and beryllium, and this is element 3, and this is element 4. So this would be 2s1, and this would be 2s2. So we're discussing the 2s peaks only. We're told this is the 2s peak. Why are they in this position? Well, if you add more protons for protons, then all the peaks shift left. So beryllium has greater nuclear charge, which is code for more positive charge in the nucleus because of the extra protons. And why is it higher? Because this represents only 1 electron in the 2s subshell, and this represents 2 electrons in it, so it is double the height. Let's talk about photoelectron spectroscopy. This is a graph of how many electrons are in a certain subshell. The first one will be shell 1s. The second will be 2s. The third would be 3p if one exists, of course. The second would be 3s. The fourth, the first would be 1s, of course. The second would be 2s if there is one. Then 2p, then 3s. The fifth would be 3p, and so forth. The vertical height represents the number of electrons in that subshell. So we can say, clearly this reached out to 3s because that would be the fourth bump here. So the 1s and 2s must be full. In fact, 2p must be full. So this is 1s with 2 in it then, isn't it? 2s with 2 in it, 2p with 6 in it. Also, this is triple the height, remember, and the height represents the number of electrons in the subshell. If this is the same height, then this is 3s2. What element is this? How many electrons are in the ground state? 2, 4, 6, and 6 is 12. This must be magnesium. Remember that Z is the proton number, and in the ground state, the protons will match the electrons. So by counting the ground state electrons, I have counted the protons, and then I can check my periodic table for element number 12. What would this be? Well, we get up to the third bump, so this must be 1s, 2s, 2p. Now, I realize that the lines are different, and you can't count on the lines representing anything in particular. This must be 1s2. So apparently 1, 2, 3, 4 lines represents 2 electrons, which means this is 2s2, which means, and be careful here, this is 2p3, because remember, every 2 lines represents 1 electron. Therefore, I have how many ground state electrons? 2, 4, and 3 more makes 7. I am looking for element number 7. Let's point out something else. 12 protons versus 7 protons. And something else they really might bring up is the binding energy. Now, the binding energy is greater to the left, which makes these graphs a little bit weird. You have to get used to them. Why is the 1s bump here at about 100 megajoules per mole, whereas this one is decidedly under? And the answer is not the lines vertically. Remember, that just represents the number of electrons in this particular graph. So these are both 1s2, but this one is not as tightly held because it is held by 7 protons versus 12. And so as the protons increase in the nucleus, all these bumps will shift to the left toward greater binding energy. So if we followed 1s2 from hydrogen on, it might go something like here for hydrogen, helium, and then it would progressively get farther and farther and farther and farther until apparently we reach this point for magnesium, and they would all be shifting left as the number of protons in the nucleus grew.